Physics at its heart is a problem-solving class, especially this class. We're learning about the rules that govern our universe, the equations that go along with them, and the best way to really understand and learn them is to work through problems that utilize them in many different ways. So this week we're going to be doing a lot of problem solving, and I'm going to give you a lot of examples, and you're going to practice some in the homework too. And one of these is a classic problem. This one is a classic problem that we see in physics classes like this. And it's an example of what we call an accelerating system. An accelerating system is where all of the objects in the system are going to be accelerating together. And when we watch the whiteboard video, I'm going to explain the problem a little bit more here. I'll give you all the variables, but what we've got is a mass here that's sliding across a frictionless table. It's connected by a cord over a pulley to a hanging block. That block is going to fall toward the ground, and it's going to drag this block on top of it with it. We're going to find the tension and acceleration of this problem, the tension in the cord and the acceleration of these blocks as a system.
We're going to solve a very classic problem that we encounter in physics to help us understand Newton's second law. Here we have a block that I'm calling capital M. This block has a mass of 3.3 kilograms right here. And this block is free to move along a frictionless surface. And it is connected by a cord that goes over a frictionless pulley right here, and that same cord is attached to a second block here of mass 2.1 kilograms, okay? This block here, the second mass, is hanging. And what we're going to do, so let's imagine I was holding it right here, and I let go of that mass. And what's going to happen is when I let go, this mass here is going to accelerate downward. It's going to slide downward. And since it's attached by a cord to this mass right here, this mass is also going to slide because of this falling mass here, okay? And so what we're going to do is use Newton's second law. We're on a frictionless surface right here, frictionless pulley, in order to find the acceleration of this sliding block right here and to find the tension on this cord. This tension on this cord is the same magnitude as the tension that's tugging on this block. It's the same magnitude as the tension that's tugging on this mass right here too, okay? So our big mass, capital M, 3.3 kilograms, our small mass, 2.1 kilograms, I'm representing by the smaller m. I've got little subscripts on them, just in case my m's start to look similar to each other. We're going to look for the acceleration of this block here, this top massive block, and the tension in the cord here. Okay, so before we even do that, let's think about all of the forces that might be acting in this problem. Okay, so here on my first big mass, big M, I've got, maybe I'll draw this in a different color. I've got the normal force acting upward here, okay? The normal force is the force that this surface here is exerting on this block, okay? And then I have the weight of this object, its mass times gravity, downward. We'll call it big M, G. And then I have the tension here on this cord. And I'm going to call this T1 right here, the tension that's pulling on this big block here. So essentially in pink here, I drew in the free body diagram for mass 1. Normal force up, tension force this way, it's weight down. And now over here on my second block, with the pink, I'm essentially going to draw in the free body diagram of the second block. We've got its weight downward, M2G, and there's also a tension force tugging up from this rope here, and I'm going to call that T2. Okay, so my object is going to fall here. The acceleration is going to happen along this direction. The acceleration is going to go in this direction here, so this block is accelerating downward, and that means that this mass is going to be accelerating in this direction. So we want to find the magnitude of this acceleration and the tension in this cord. What are we going to do first? Well, here's a very important thing that we want to think about before I even start writing down these equations. Because these masses are connected by the same rope, that means that the magnitude of T1 equals the magnitude of T2. It's the same rope, same tension. And we're just going to refer to that then as T eventually. And because these objects, both of these blocks, are connected by the same cord, the magnitude of their acceleration is going to be the same, okay? So I'll say that the magnitude of AX equals AY. That's just the magnitude, and I'm going to set that equal to A, okay? So AX and AY, the magnitude of them will be the same, but their direction might be different and will be different because this guy is accelerating negative y direction and this one is accelerating the positive x direction. But the magnitude will be the same, so we'll just set that equal to A. Now that we've set up the problem, we can apply Newton's second law. Let's think about our big mass right here. This mass is only moving in the horizontal direction. So if we think about the sum of all the forces in the horizontal direction on my big mass, we've got the sum of the forces equals the mass times acceleration. The only force acting on our big mass in the horizontal direction is tension, and it's in the positive x direction. So T1 equals M1, and I said that the magnitude of the acceleration in the x equals the magnitude of the acceleration in the y, and we're just calling that A. So I'm just going to say that that is equal to A. And over here, for the sum of my forces in the y direction equals our second mass times its acceleration in the y direction. Because our second mass is only moving in the vertical direction, so we only have to solve Newton's second law in the vertical direction for this one. And this hanging mass has two forces acting on it. It's got the tension force upward, T2 upward, minus its weight, minus m2g acting downward, equals its mass, and this acceleration is in the negative direction. It's falling downward. So we said that the magnitude of the acceleration in the x is equal to the magnitude of the acceleration in the y is equal to A. So here, for the acceleration in the y direction, I'm going to say that that's minus A. The magnitudes for both of these accelerations is the same. The x1 is positive, but the y1 is negative. So that's why I put that there. Okay. And we also said that we can say T1 is equal to T2 is equal to T. The tension pulling on both of those objects is the same because they're connected all along one same line, okay? All along one same cord. So this is just T is equal to M1A, capital M, and T2 we'll just swap out for T, minus M2G equals minus M2A. Okay, so now we have two equations. We have two unknowns. And so what we have to do, let's do this. We want to solve both of these equations for T, the tension, and set them equal to each other. And then if we do that, then we solve that final equation for acceleration. And then we've got our acceleration. We can take that acceleration and plug it to any one of these two equations to get the tension on the blocks, okay? So this one is already solved for T. Let's solve this equation for T. If we do that, T is equal to M2G minus M2A. All right, so now we can set both of these equal to each other, since T1 is equal to T2 is equal to T. So then we have big mass, M1, times acceleration equals m2g minus m2a. Okay, so we're setting t equal. All right, and that's what we're doing right here. Now we know m2, we know big M, and we just need to solve this equation for acceleration. If you really like algebra, then this section of the class is going to be really exciting for you. We're going to do a lot of algebra here. So I need to get all the components with the term of a on one side. So I'm going to move m2a over to the other side. So I have m1a plus m2a is equal to m2g. Okay, so what I can do, I've got both of these terms on the left-hand side are multiplied by a. So I can factor out an a. A times big M plus little m is equal to m2g. Now I divide both sides by big M plus little m, and then my acceleration equals m2g over big M plus little m. Okay, so that's the equation. And then now that I've derived that equation, all I have to do is plug in the initial values that I'm given. This is why I really love to solve equations algebraically, because you solve everything with just the variables, and then in the final step you can plug in the numbers. That means you can reuse this equation anytime you solve a same problem. Reuse this equation, just plug in new numbers each time, but you know if you've derived the equation correctly, then the answer is always going to be correct too. So you can reuse it many times. So let's plug in the numbers. Our smaller mass is 2.1 kilograms. And we're multiplying it by acceleration due to gravity, 9.8 meters per second squared. And then we divide it by our big mass, 3.3 kilograms, plus the small mass, 2.1 kilograms. And then we find that our acceleration is going to be 3.8 meters per second squared. Okay, so that's one part of the problem. That's our acceleration. This block is moving to the left with that magnitude of 3.8 meters per second squared. Acceleration, this block is falling downward with the magnitude of acceleration of 3.8 meters per second squared. What's the tension? You could take 3.8 meters per second squared for acceleration and put it into any one of these two equations, and you'd get the same answer. So let's just do the simple one. Let's put it into this one right here. So if we do that, tension is equal to our big mass, 3.3 kilograms, times our acceleration, 3.8 meters per second squared, and then I find that the tension is equal to 12.6 newtons. Okay, and then if you wanted to just always check yourself if you're solving a problem like this again, you could take that acceleration, plug it into the second equation for tension, and hopefully, if you've done everything right, you will get the same tension as you did on the first block. You'll get the same tension for the second block here.